Is I'm audible, right? Yeah. Hello everyone. Good afternoon. I welcome you all for the lecture 5 on the day 2 on the GAN course on hybrid renewable energy system in microgrids. Now I'm going to deliver on the power quality issues mitigation in microgrid. Yeah, I try to introduce some of the power quality definition or power quality issues and what are the different kind of devices which will be used to improve the power quality in microgrids. Yeah, when you look the definition of the power quality, uh, the power quality is a set of boundaries that allows a system to work in its intended manner without any significant loss in its performance. If you take a load like the desired output or the performance, if it is not, it is giving to be a correct as load to be performed, then we can say that the system power quality is well maintained. It all depends on the power quality, which is defined with respect to the load also. Okay, as the load characteristic is expected to deliver out, then we can say that the quality of the supply is good. The term electric power quality is generally used to assess and maintain the good quality of the power at the level of the generation, transmission, distribution, and utilization of an AC electric power. Yeah, how do you classify the power quality problems? It is with respect to the voltage and current and also the frequency. And you can define the power quality with respect to the transient and the steady state performance. And the power quality issues also can be there with related to the supply and also with respect to the load also. These are the some of the standards or some are the important standards which they define the power quality terms. Uh, we used to generally follow the IEEE 519, but is the extended version of IEEE 519 and 1159 is 1250. Okay, you have what are the definitions and what are the power quality power quality standards with respect to the uh, ranges of the voltage also. You can also refer to the standards with respect to the microgrid, as Professor Saad has explained the different types of the microgrid control and the nature of the microgrid with respect to the grid connected mode and islanding mode. There are different standards out there. You can get it this particular 2030. And coming back to the IEEE 115, they have categorized with respect to the duration of the voltage magnitude and then the time duration of the voltage. Okay, I'm not going to emphasize more on this particular definitions. Uh, um, yeah, the majorly like the transients which are used to occur due to the lightning or lightning in this lightning phenomenon in the system, and you have a short duration RMS voltage variations. I mean, it all depends on the time. Okay, and you have a long duration voltage variations, and then an imbalance in the voltage and the current, waveform distortion. The waveform distortion is referred to the harmonics. Okay, it is not directly related to the harmonics. It all the combination of harmonics, interharmonics, notching, noise, and DC offset. Okay. Uh, I'll try to talk about on the waveform distortion. It is basically like the majority of the distortion which will try to exist in or occur in the system is due to the nonlinear loads. Okay, and the voltage fluctuations where we have the intermittent nature of the load. Because of that, you are going to have the voltage fluctuations, and then the power frequency variations. Yeah, these are the typical power quality issues, and they're defined with respect to the magnitude and then the duration, and then this particular case of the transients they define with respect to the rise time. Okay, and the frequency also. Yeah, These are some of the power quality issues in microgrid, which will try to occur in this particular microgrid system. The fault in the system are in the load side. Okay, maybe the load is also get affected with the fault, and also the system. Maybe the short circuits and the open circuits, insulation failures. These are the three things which contribute to the faults. And with the fault, like you have affect the voltage, and sometimes it may affect purely outage of the system also. And the load issues, when you say load issues, it tries, I mean, if you have unbalanced loads and overloading also, and nonlinear loads, as I said, the harmonics due to the nonlinear loads, and the reactive power. These are the uh, uh, effects. Because of that, because of the load, you will be having the power quality issues. And then improper rounding, where it tries to create the noise in the system, and also that is going to affect your current also, maybe the voltage fluctuations also. This leads to the malfunction of the equipment. And yeah, the lightning phenomena, which is going to create the transient over voltages also. And yeah, next is the intermittent load changes, which will causes the voltage fluctuations and even the frequency fluctuations also. Okay, but anyway, the frequency fluctuations is not more with respect to the intermittent. Whenever you have the high impact of the load, then you having going to have the frequency fluctuations. Yeah. The last point of this intermittent power generation from renewable energy sources, this is this particular issue which will be going to have exist with respect to the microgrid. The above all are maybe the five. There are commonly uh, issues which arises in the distribution system also. Okay, when you talk about the intermittent power generation, that is whenever you have a microgrid system, you are going to have uh, the effect on the voltage and the frequency instabilities in the microgrid. Okay, but when you take about a distribution system, this won't come arise because your distribution grid is very what to say a stiff source. Okay, so it won't have a effect on the voltage and the frequency. Yeah, these are the issues which are come arises in the microgrid. Uh, yeah, if you want to mitigate the power quality issues in the distribution system or in the in the microgrid, you have a custom power devices, where the custom power devices is again coming to the a power electronic voltage source, a power electronic device, where basically you are going to use the voltage source input. To mitigate the power quality issues, we can also have another alternative arrangements. Suppose if you take a lightning phenomena, you have an arrestor also there, lightning arrestor. With that also we can try to, I mean, suppress the over voltages, or impulse voltages also. Yeah, this particular custom power devices are very, very specific power quality issues we can tries to mitigate or improve also. Take a D-STATCOM. Yeah, it tries to mitigate the current related power quality problems, such as the power factor correction of source side and the compensation of excessive neutral current, and compensation of excessive neutral current, load balancing, and also the harmonics. Okay, the D-STATCOM, the distributed static compensator. The dynamic voltage restorer, it is going to take the voltage at the point of common coupling, which are both are transient and the steady state. But in general, the DVR, which is said, the dynamic voltage restorer, is going to take uh, the transient effect only, not under the steady state nature. We'll see why it cannot be used for the steady state and what is required to be added to the more to the to get a steady state improvement also. And the last one is the unified power quality conditioner. It is a combination of the D-STATCOM and the DVR for mitigating simultaneously both the current and voltage related problems. Okay. Yeah. But in general, like the most of the voltage related problems, apart from the steady state problems, The transients are there for a very short duration of a time, uh, and also it doesn't, maybe if you are going to take about a very sensitive loads, uh, especially I mean, as Professor Saad has discussed about the sensitive loads, maybe the data centers, maybe the semiconductor manufacturing industries, maybe like the hospital loads also there. For those things, the DVR is very well used also, but typically in the existing the DVR, I mean, people are not going to use the DVR. Yeah, and I mean, if you have any doubts, you can ask now, so that we'll try to move to the using the power quality improvement by, I mean, by passive filters. Yeah, we just discussed about yeah, some of the power quality definitions, not so elaborative. The definitions are we not discussed it. We just have discussed about what kind of the power quality issues exist in the microgrid. Okay. Yeah. Now we try to see that the passive filters which can be used to improve the power quality. Okay. Yeah. I mean, this particular presentation has been prepared from by taking these four references: passive filters and power system harmonics, and passive filter design. Okay. Yeah. Uh, we will try to discuss on why this passive filters are required with respect to the harmonics elimination. Okay. And these particular passive filters, which can also be utilized for to eliminate the voltage rated harmonics also. Whenever you say a filter which can be utilized to eliminate the harmonics, or it can also be utilized at the fundamental level also, not necessary to be harmonics. Okay. I mean, this particular slide, which shows that especially the fourth equation, you can say that this is a PF1, which is there, the power factor 1, which is a displacement power factor. And when you have a nonlinear load, you have the power overall power factor is going to be affected also. Okay, because you have a TST in current and TST in voltage, and both. Suppose if your power factor is around zero point 0.9, PF1, which is zero point 0.9, with this factor it is going to be decreased further. Okay, what I want to highlight over here is when you have a harmonics, you are going to lose out your power factor also. Yeah. And now with this particular slide, which I want to highlight, is when you have a load, load is carrying the load average power as well as the reactive power, then your terminal voltage, this is the V, which is going to be affected because of the drop in the source impedance. Okay, so this equation, maybe you can see over here, the QL is going to affect this particular drop. Okay, anyway, this particular, I mean, when the QL is zero in this equation, you are going to have the drop across RSPL by V and JXS by PL by V. What the delta V is nothing but it is going to be calculated the drop across your ZS and IL. Okay. And what I want to highlight over here is because of the reactive power, it is going to have an effect on the on particular to the terminal voltage of V. Okay. So uh, yeah, you can I mean, when you say about a passive filters are used to reduce the harmonics, and capacitors are generally employed to improve the power factor of the AC loads. Okay, this is the purpose. But when you say the passive filter is the combination of the passive elements, inductance, capacitance, inductor, capacitor, and resistance also. Okay, and the passive elements are used to tune the voltage harmonics. I was mentioning that it need not be to eliminate the current, but it can be used for the voltage harmonics also. Yeah, we see that some of the classifications and the topologies. What are the different types of the topologies based on the element connection and the connection based classification, supply based classifications. Okay, these are the three types of the shunt, series, and hybrid. Where a series, in the sense like you have a connection of the elements which are, um, yeah, in this particular. Okay, we have a series connection of this. When you are going to have the shunt, we are going to have connection with the line. Okay, and you can also have the hybrid filters where we can go for both the combination of the series and yeah, this particular maybe I'll try to show you. Yeah, this particular case where we can go for a hybrid filter also. Okay, we have a series as well as the hybrid also. Okay, yeah, we will be seeing the slide, especially this particular thing. You can see that the impedance plot with respect to the frequency. Okay, how you know that how it is varying. Okay, I mean considering this particular combination of the figure here, which is connected in a shunt connection. Okay, yeah. Now, with respect to the frequency, you are going to have the change of the L and C values. This is going to be the reactance of the inductor and the capacitance are going to change. At this particular frequency, you can see this point at this cursor. Okay, you are going to have the impedance is very low. Okay, in all other cases, the impedance is very high. Okay, that means that at this particular frequency component of the current, which is going to offer your a low frequency, I mean at a low impedance. So that means that it is going to short maybe. Okay, it is going to provide the low impedance. So the current tendent to flow in this particular direction of this particular frequency component wherever you have the lower impedance. Okay. This you call it as a band pass filter. Sometimes this particular B is called a high pass filter. You have a double band pass filter and composite filters. Okay. Yeah, I'll be showing you one of the simulation file where we try to eliminate one of the frequency component. Okay. Yeah, here without excluding this particular series RLC branch, we are used this one as a mm, I can say that an LC filter also, maybe having out the internal resistance. We'll try to see that. Suppose if AC source, this particular diode rectifier load, a full bridge diode rectifier load, is excited with the AC source. Now, when you try to excite with the AC source, you got the current this nature. Okay, you have the current of this nature. When you see the harmonic spectrum, you can observe like the total harmonic distortion is around 22.63 and the fundamental is 38.18. Okay. Now, what we try to was when you observe here the harmonic spectrum, the 150 hertz harmonic frequency, this is 100 hertz, this is 150. Okay, you won't have the even harmonics, okay, because of the half wave symmetry. You will be having the odd harmonics 150 and then 250. This harmonic is approximately is equal to 20 percentage of your fundamental current. Okay, now what is our aim was we use some passive filter to eliminate this particular harmonic current of the third harmonic. Okay, yeah. Now the equation was what the way which has been designed in the consideration is You have the voltage is 230 volts and power is the real power which is taken by the load is 4.9 kilowatt, and it is 2600 var, not kilowatt, it is a var, 2600. What we tried to use was this much amount of the reactive power of 2600 kVr is required by your the diode bridge rectifier. Okay, full bridge diode bridge. We consider the combination of the series RLC branch is to support 2600 kVr. Okay, when we are going to use this particular filter, a passive filter, to improve the power factor as well as uh, to eliminate the third harmonic. Okay, we are going to have a design. So this is the equation where you can find out the X filter of V square by Q, which we get the fundamental value of the reactance, fundamental value of the filter reactance. The reactance is a combination of the capacitive and inductive reactance Xc minus XL into X filter. And this particular equation of H square, what we are what is going to have H is the order of the harmonic elimination. We can able to find out. What is this sort of an equation is, we were trying to have the at a third harmonic frequency, the capacitive reactance of the third harmonic reactance, which is equal to the third harmonic inductive reactance. Okay, we are going to make the effective reactance of the series RLC branch is very low. Okay, so with that equation, we try to make out this particular equation. If you substitute in this equation, maybe you can substitute the value of XL is equal to XC by H square, you get this equation. Okay, we know the X filter by substituting the reactive power what it is and the voltage also, and knowing about the elimination of it is third harmonic, you get the value of XC. Okay, and whatever the XC which is there, it is fundamental level. Okay, once you find out the XC, we can evaluate this particular value of the XL also. Okay. Okay, now the design values for the third harmonic, which you get L is equal to 8.1 millihenry and C is equal to 139.13 microfarad. Okay, when you are trying to simulate again keeping these values of, I mean, this particular waveforms is without before passive filter connection. Now we are connected after a passive filter. In this, the observation over here, the load current, when you see this particular load current also, the peak value is somewhere around 38 or 39. Okay. Here also the same thing around 36, 37. Okay. The load is the same. You can see this is a filter current which used to flow with a passive filter. Okay, now the source current is somewhat looks like not what exactly the real load current is source current. It is the current has been changed over here. Okay. Now when you do the harmonic analysis after the passive filter, we are going to get around 14.51 the total harmonic distortion, and we can see in the harmonic spectrum at 150 order there is no magnitude over here. Okay. We try to eliminate that harmonic component. Correct. And if you see around fundamental current is 34.1. Earlier the fundamental current is 38.18. Okay. The reduction of the fundamental reactive fundamental current is because of the passive filter is designed to support the reactive power also. Okay. Because of that, you have around 34.1 over here. Okay. With this, like you can understand like how the passive filter is used in this connect in this system to improve the or to eliminate the third harmonic. Yeah, these kind of whatever I'm just highlighting the passive filters to eliminate the third harmonic and the reactive support can also be used in the your microgrid. Okay, in the microgrid, see you, in day-to-day life you have a different kind of a power electronic loads or the nonlinear loads. So these kind of the current also will be there in a system also. One thing is like with the what is the first the major impact when you are going to allow the nonlinear current in a system is we are going to underutilize the system. It is by observation of the power factor. Power factor is going to reduce. Okay. Yeah, we can go this particular kind of a design or any kind of a design with respect to the what to say the double tube filter also, where we can, if you want to go for the double band pass filter also, we can go for, or else wherever you want to go for a band. One thing is you can try to assume one of the value of any kind of L or C, and then you plot about the frequency, how it is going to change the response also. Okay, when you're going for a high pass filter. Yeah, now what I see, it is not just the design of the passive filter. We need to look the some of the considerations. What are the considerations are? I'm just, is there any doubts over here up to here? Please let me know if there is any doubts.
No, sir.
Hello.
Yeah.
Yeah. Yeah. Yes. Actually, you're using the passive filter, no? So only here showing the how much THD is reduced. Okay.
Yeah, yeah.
And if you adding the passive filter into the system, so that means you are adding the impedance also, right? That impedance angle also should be present. No? That
Which one?
sometimes value should mention like this is the level like that. It shows like that also. So if exceeds, then the voltage also will be very high. That impedance value of that when we adding the passive filter.
Impedance angle, I didn't understand what do you mean the impedance angle.
No, sir,
See, I understand that there is the passive filter also having an angle. Yeah, correct.
yeah, yeah. So that
Sir,
time actually impedance values also will be going high, very high. So we
sir,
have
he is asking
impedance
about the resonance.
resonance point. Yeah.
Resonance he is asking.
When we adding the passive filter, some of the point it will occur the resonance also. So
No,
that
no, yeah, yeah, yeah.
resonance,
It is in fact like see the impedance angle. Uh, See, I don't know how the impedance angle is going to affect. What I want to highlight is whatever you said, like, it is going to operate at the resonance only. When you are going to eliminate, when you look this particular equation, the x is equal to this sixth equation. What we are trying to do was we are going to make the impedance with respect to the third harmonic is very small or very negligible also. With respect to all other frequency component is going to offer the high impedance only. Okay.
okay, okay. In a graph we can see the impedance values also. In the impedance value at the time we are adding the passive filter, maybe third order. Only you are sizing for third order. Okay, so that third order, how much value will be there? That impedance value that we can see in the graph, only
Impedance angle.
current value. Yeah, impedance ohm. It shows ohms value actually.
Ah,
Maybe if you get an ETAB or some other diesel and power factory, we'll get to know that things, I think.
sir, can you speak it louder, sir? I mean, I'm not able to get your.
Okay, so yeah, when we adding the passive filter,
Okay.
okay, in the system, so that time impedance also will be high. So that ohm will be creating in the system to resonance. So that is within the limit or not that we have to check by graph. But here it's showing only the current wave and harmonic harder values that how much it's reduced. That only it's showing. So what about the impedance value that I'm asking? So the system, what about the impedance value?
Okay. Okay.
Yeah.
Yeah. Actually, see, I mean, this particular plot of yeah. You were asking about this particular plot, maybe the angle also, whatever it may be. Uh, See, this plot, what we have plotted is, it is a plot of the taking at the frequency, how the overall impedance is going to change with respect to the frequency. This is the plot which is going to be highlighted in this particular plot. See, at the different frequencies of omega, when you take about LC alone, it is going to have the XL, what to say, the difference of XL and XC, right? Maybe neglecting about the resistance. Okay. you are going to look over overall how the impedance or impedance magnitude is going to change. Okay, the current which is flowing this particular plant is majorly dependent on the impedance only, overall impedance. Okay, it is like whatever you are showing about looking over the figure A, it is like a resonance graph only. At this particular point, your system is going at this particular frequency, the resonant frequency. At the resonance frequency, it is going to offer only the resistance value. Okay, yeah. And looking back to this particular graph of the voltage and the current, we are see in this particular current, you have the frequency components. Okay, the current, the load, the current, whatever it is there of the rectifier side, the current which is drawn by the from the source is going to have one first harmonic and the third harmonic and the fifth and the seventh harmonic, which is trying the load is going to draw that current, or some cases where you show that nonlinear as a current source also. It is going to inject the current harmonics. Okay. See this particular frequency component which will be there in your source current. Okay,
Okay.
and then when you are going to use when you are going to have the filter, what exactly when you look this particular filter current, it is going to have the fundamental component of the current. This filter current is going to have the fundamental current, and then like you are going to have the third harmonic current. See, in this particular graph, it is not required to show the impedance graph with respect to the time varying. See, your impedance for this frequency, for that, I mean, over a time, whenever you stay about a 0.2 and 0.5, the impedance for the different frequency component, it is not going to alter. It will be the same only. Okay. And then in this particular graph, it is not required to show the impedance graph with the frequency. Okay.
Yeah. Okay, sir.
Shiv Kumar sir,
Yeah.
let me tell you one thing. What he was asking about is actually in the power system softwares like ETAP and Ditch Silent softwares.
Mhm.
So there is an option whenever we do harmonic analysis, there is a option for plotting this impedance, what resonance impedance, what we are seeing, that versus the harmonic order.
So impedance versus harmonic
Yeah,
order.
same resonance plot what you had shown. Instead of
Mhm.
omega, we'll be getting that x-axis as the order of the harmonics.
Okay, okay. And y-axis will be
Y-axis will be the impedance only, magnitude.
okay, not the angle, right?
No, no, not the angle. Actually, that's how it is represented.
Uh-huh.
That is, it is called as a angular plot only, but
Uh-huh.
it is the impedance only.
Okay, okay, okay.
So
Maybe
that
that
is
one.
what he was referring. So that
Uh-huh.
also can be plotted, but here we have to extract the values and plot here in the MATLAB.
Uh-huh. Yeah, correct. Okay, okay. I mean, okay, I got it. I got it.
Yeah, yes, sir.
Any other questions? Yeah, I think like we can go ahead. Yeah. Yeah. Without see this particular passive filter, we have just shown the example to eliminate one of the harmonic. Uh, And once after designing the filter, it is not very so easy. Okay, there are other factors need to be considered. I'm just going to uh, quickly, I mean, show you like what are the other factors need to be evaluated. Yeah, this is the standard of IEEE, a standard of 18-2002, where once after designing the filter, we need to estimate the peak voltage and RMS voltage and RMS current and the KVR. Okay. I mean, once you design a filter, it is like we have seen the impedance plot with the frequency, right? It is showing some impedance with respect to other frequency components also. That means that it is going to allow the other harmonic components also. Because of that reason, we need to look over what is the maximum capacitor when the peak voltage to be allowed to be 120 percentage, and RMS voltage is 110 percentage, and RMS current is 180, and the KVR is 135. Okay, this is the percentage need to be allowed. There is a case study. I'm not going to give that case study. I mean, I'll just give the case study what exactly it is. See here, the kVA rating of the load is 120 with a power factor of 0.75. This particular load is approximately carrying about 30% of fundamental current with a maximum of 25% of fifth harmonic. Okay, and you have a transformer which is of 150 kVA and it is a 6% impedance. You have a fifth harmonic background voltage distortion. You have a fifth harmonic in the source voltage also. On the utility side of transformer is 1% of your fundamental. For this, actually, I show you like some of the things what how they have calculated here. Is one of the. I'll try to show you the RMS current. This is the RMS current with respect to the fundamental and the harmonic. Okay, and yeah, you can see that the capacitor is going to have the fundamental and then the harmonic voltage. See, we need to estimate these particular capacitor peak or the capacitor RMS voltage with respect to the fundamental level as well as the harmonic level. Why it is so? The fundamental and harmonics is we are not just connecting a passive filter to eliminate one of the harmonic. We are just making use of this particular passive filter to improve the power factor as well as the dominant harmonic which is going to be there in the exist. Okay, because of that reason, we need to calculating the fundamental, calculating the RMS value, overall RMS value, RMS current, and the peak voltage also. Okay. Yeah, this is one of the flowchart of the design of the single tune filter. If you want to design a single tune filter, any kind of a filter, what we should require is we require to thoroughly understand what kind of the nature of the loads are there in your microgrid. Okay, what nature of the loads are there, nature of the loads, and the harmonic spectrum at the level of a point of common coupling. Okay, with that, like we can understand like what is the dominant harmonic, how much is the capacitive reactive power required for your in a microgrid. Okay. Suppose if it doesn't have the capacitor requirement, we can go for design a minimum filter, whichever is the dominant. If it is there, then we need to go for design of the capacitor, and the capacitor also we can go for switching steps also. I mean, we can have the discrete kind of a capacitor bank connections also. Okay, yeah, with that also we can go. And once you design the capacitor bank, whatever we have done, the power factor improvement with respect to the just now the case study, we can once after designing the capacitor, we need to go for a passive filter. Passive filter in the sense like we need to go for equating the capacitive reactance to the inductive reactance. Okay. Once after that, we need to eliminate the harmonic power flow calculations. Okay, like how much is the harmonic power is injected to a system also. Yeah. Once after that, here is there is TDD is acceptable. Okay. We have seen like the TSD, but generally like in a typical system, we need to look the total demand distortion apart from the TSD. TSD is not so essential required for if you are going to use for the current harmonics. Okay. We need to look for the is TDD is acceptable. See, once after designing the filter, we need to estimate like is your TDD is acceptable. If it is yes, then what we have to go for is harmonic field current loading on filter components acceptable or not. Okay, all the current related loading we need to estimate it. If it is yes, we have to go for a voltage rating is acceptable or not. If it is yes, we can start this design. If it is no at the harmonic current loading requirements, as we have seen like the RMS current, okay, this RMS current loading, it is not matching, then we need to go for the redesign the filter. Okay, increasing the kVR, add parallel filters and change filter type. These are the things. Okay, and if it is not the acceptable voltage limit, we have to increase the voltage rating of your capacitor. This is a flowchart which can be used in designing your single tune. Okay. Is there any questions with respect to this slide? Now what we do was, see, the disadvantage of going for a passive filter is, one of the disadvantages is a detuning of the filter over a time period. The capacitor or the inductor nature is going to change. So because of that, it may not be uh, tuned to the eliminate that particular harmonic. Because of the aging, you have a tendency of the detuning also. Maybe this particular filter, passive filter, is also trying to create a kind of a resonance with other frequency components also, because no, because of the change of the overall impedance at the load side and the source side. Maybe we need to look over the Thevenin equivalent impedance, which will be going to be in parallel with your filter. Okay, because of that also there may be a kind of a resonance problem. Because of that, we will be going for an active filters. Okay, we'll see that now. An active filters. Okay, what we are trying to look over now in this particular presentation, in this particular slides, are we are going to eliminate the current harmonics. Not only one of the harmonic, we will try to eliminate the multiple number of the harmonics by making use of your active power filter as well as the reactive power support also. Okay. Yeah, here the waveform which shows that a nonlinear load, how you are going to have the currents. This is a figure of A is the fundamental, and you are going to have the third harmonic, and then the combination of the 1 and 3, we are going to have the first and the third harmonic. This is the nonlinear load currents, and yeah, you can see that the A of figure 2 of A, it's the balanced voltages, and the figure B is the unbalanced voltages. This unbalance of the voltages, as I was mentioning of the load unbalance, right? In the beginning of the power quality issues which try to exist in particular to the microgrid. The unbalance because of the uneven connection of your loads also is going to create this particular unbalanced problem. Okay? Uh, yeah. Now, this particular figure which is showing to have a three-phase, four-wire system. Maybe you can consider this as a microgrid also. Okay, not towards to the this you have a source. Forget about what kind of a source which is connected over here. Okay, you can see this particular case we are consider a three-phase, four-wire, balanced, unbalanced. We have a fourth wire is a neutral wire. Yeah, this is a three-leg VSC with split capacitors. And yeah, this is what is used over here, particularly this STATCOM is this particular inverter, the voltage source converter, used to provide the harmonics current. Okay? Whatever the harmonic current is required for your three-phase, four-wire balance and balance load, are not necessary to be harmonic. It also supports the reactive current also. Okay. Yeah, the reactive current. And why? What is the what? Once you supply the reactive current from your this particular three-leg voltage source converter, we are going to make your source current of ISC and ISP and ISC having about the only the fundamental component of the current, not the harmonic component of the current. What is the advantage of going for it, making out this particular current is balanced or perfectly sinusoidal, having a fundamental current? We are going to improve your source power factor. Okay, what is the advantage you make the source power factor unity? Okay, what is the advantage of you making about the source power factor unity? Anyone? Yes. Okay. I mean, forget about the source power factor increment. Why we use a power factor correction in general? Why use a power factor correction in general? Anyone?
Sir, reducing the THD.
Pardon?
Reducing THD, my total harmonic distortion. Reducing.
No. Oh, yeah, you mean to say that reducing the THD?
Hmm.
No, I'm asking about. See, you will be connecting the power factor correction of the capacitors, right? What is the purpose of it? Why we do that? The power factor correction. The THD, the power factor correction doesn't make your THD less. That is the first thing which you need to understand. Okay, power factor correction can be done by making use of the simple capacitors also. Okay.
Yes.
Yeah, what the first, the basic important point is like you are going to utilize your source in an effective way. Okay, this particular source is there, right? You have a source over here. The source is utilized in a effective way. In the effective way, in the sense like when you see the power factor definition, it is P by something of S. The S in the sense like if your source is supplying only the real power, assume that, okay, S is equal to P. And what it signifies is the source is only sending about the real power. That means that you are going to utilize your source in an effective way. Okay, if you're not allowing any kind of a reactive power. Suppose if your denominator, if you're allowing any reactive power, your factor will be very less, maybe 0.8 or 0.6. That means that you are not utilizing it in a proper effect. Yeah. Now what we look into is, see, when you look into this particular diagram, it shows that this particular current IF is your one leg of a three-phase VSI. Here you can see that this is the load current. You can see this is what the load current is. What it is trying to do was when you try to have your filter current, harmonics are there. And see, now the IS has become a very sinusoidal. It's just to have the understanding what we are going to use your the distributed static components. Here, what this particular control block diagram, where your inverter leg, which is controlled by the hysteresis node. Okay, it is based on your the filter current. I mean the error between the reference filter current and the actual filter current. Okay? Yeah. See, if the distorted load current allowed to the source current, the other loads connected to the same source are get affected, because once you allow the harmonics, it is trying to pollute this the PCC voltage. Okay, because of that, like it is not going to give a satisfactory performance. Yeah, this is one of the theory which has been used to see. We need to generate what is the filter cut, how much it is to be injected. It is not just uh, make out yourself a sinusoidal current. Okay, it is based on your what the load current is there. We can't inject any kind of a current with the T-STAT-COP in order to make your source current to be a sinusoidal. Okay, we need to know that what is the reference filter current. This is one of the theory where the instantaneous symmetrical component theory, where this particular theory which will be used to generate your reference currents. Okay, I'm not going to tell you much about this particular theory. Okay, what it is trying to make sure that is, it is going to make sure that once after taking about these voltages VSA VSB to a balanced voltages, and the load average power is 3 by 2 times of VMIM. We are not considering the P loss term also. We're just considering it is going to be taken as 3 VRMS IRMS, right? If we eliminate this 2 as a root 2 by root 2, which is going to give the RMS values. Okay. Yeah, it is just taking out these equations, the voltages, instantaneous voltages equations, substituting over here and considering the P loss term to be 0, and the PL average is the load average power is 3 by 2 times of PM. The load average power is the equation is 3 times of VRMS into IRMS. Okay. Yeah, once you substitute it, you get about these currents. Okay. The ISA is equal to Im sin omega t, and ISB is equal to Im. These are the reference source current, which are expected when you are going to use the distributed static components. Okay. Now you get a filter current by subtracting from the load current of ILA minus ISS star. Yeah, this is the overall control of the voltage source inverter to improve your current quality, the source current quality. Now we look how the hysteresis current control is going to operate. Okay, here is your reference current, the solid line, and the dashed line is the upper limit of H band and L band. Okay. I mean, how you are going to estimate these currents is when IA star is going to touch to the upper band, we need to push again back to over here. What mean to say that how you push the current when you look the current over here. Yeah, here this is the current. When you try to turn on this particular switch, the top switch of this particular leg of maybe you can see that the A phase. This is the A phase. You can see that whenever you want to have the a positive current to be increased, then you need to apply this voltage. Okay, this is the way which it is going to operate. When you want to pull the current, what we need to do is we need to apply the lower voltage, right? This way. Yeah, we need to apply the negative voltage. Negative voltage is applied over here. This sort of an operation which can be done by the hysteresis. We can see that SW1, when it is pulling down, we are just applying the 0.5 volts to the top switch. Okay? When we want to pull down, we need to apply the bottom switch. So this is the way which the advantage of hysteresis current control is easy to implement and fast response. Apart from that, we can able to protect your switches in drawing about any higher currents also. Okay? We can limit your current not exceeding more than this upper limit or the lower limit. Okay, we can able to protect your if there is any short circuit happen in the load side or maybe at the load side, it won't drive that current also. Okay, suppose if you are operating in the PWM kind of a mechanism, we can't limit the current. Okay, it may capacitor may not it discharges also. Okay, yeah. We also look now how does the basic single phase split capacitor T-stat works. Okay, what is the purpose of this diode of D1 to the switch and diode of a D2 of the switch? Now, what we looked is we are not giving the switching pulses to S1 or S2 also. Okay, or else maybe we try to give the switching pulses to S1 and S2 also. Okay, yeah, without having any kind of a switching pulses, the charging parts of the DC capacitor without the gate pulse applied to the T-stat. You can see over here, even though when you don't apply the switching pulses to the S1 and S2, the conduction, see that the diode is conducting. Okay. When this diode D1 is conducting, anyone? When this diode is going to conduct? Okay. This is like a simple a rectifier. Okay, when you have a positive cycle, it is going to, when there is a negative supply of the voltage, the D2 starts conducting. Okay, this way. Okay, this is a charging mode, and this is also a charging mode. You can see this particular voltages. You can see that we have measured it. Our IDC1 during the positive cycle, and during the negative cycle, the IDC2 current is going. Yeah. It's again going to diminish. The current of IDC1, IDC2 is going to diminish. There is a filter current actually. This is the voltage which is going to be charged at the peak of your supply voltage. Okay? The capacitor is going to be charged to the peak of the supply voltage. Yeah, now I try to show you like how does the switching operation is going to operate during the hysteresis current control technique. Okay. Yeah, now I mean why we are going to look this particular kind of a mechanism is, suppose in a microgrid, suppose if you want to inject any kind of a reactive power support in order to improve the voltage. In that case, like we can use this particular distractor. The distractor used to eliminate the harmonics as well as the unbalanced current as well as the reactive power support also. Okay. For that, like in a microgrid applications where you are going to operate one of the control is the hysteresis current control technique. Okay. The hysteresis current control technique has its own advantage. Like one of the advantages, we can avoid allowing the short circuit current to the switches also. Yeah, here when you are going to operate in the positive cycle of the IF current, the reference current is positive. Okay. Now the DIF by dt having the positive slope. Okay, having the positive slope. That means that this kind of the operation, you have a positive slope of your filter current. Okay, you have a positive slope of the current. This operation, what we are trying to do was we are trying to conducting devices S1. Okay, conducting devices S1. During that period, you have a DC link capacitor voltage is discharging mode. It is going to be discharging mode. When you try to pull the current of having the positive slope to the negative slope, you are pushing out the negative slope. Okay, then what is going to happen is df by dt is negative, less than 0. That means that d2 is conducting. See, the first and the second column, it tried to show that the current is going to be a positive current. During that period, only the switches S1 and T2 are conducting. During the negative slope of the current, even though if you are going to give the switching pulses to the S2, S2 is not going to conduct. The T2 alone is going to be in the operation. Okay, yeah, D2 start. When D2 is conducting, it is a charging of a CDC1. Okay, charging of a CDC1. So that means that, see, now the D2 is conducting in the sense like it is in the charging mode, right? Okay, when your switch is conducting S1, you are going to have the discharge. So this is the kind of the operation which will be there of the D start come. During the negative cycle, the switches which are being conducting are the D1 and S2. Okay? D1 and S2. Yeah, you can see this operation over here. You have a filter current which is of sinusoidal. Okay, the reference filter current is sinusoidal. See, when there is a positive cycle over here, we have the conduction of it. The switches are the S1 and your D2. You can see that during the positive cycle, this here. Okay, you have a conduction of S1 and the D2. There is a small leakage current is there through the diode. Okay, D1 when your switch is maybe you have a small leakage current over. Okay. And during the negative cycle of the reference current, you can see that the diode D1 is conducting and S2 is conducting. Okay, this shows that like how your switches of your voltage source converter is going to operate. You can see that this voltage is here. When you have to see maybe the solid one is going to be shown the VDC1 voltage during the positive cycle of the current. What I said, like it is discharging, right? Maybe slightly, maybe here it should be in discharging mode. Maybe the labeling has not been done properly, but VDC1 is in discharging mode, right? What is written is charging, but it should be charging. Maybe the labeling has not been done properly over here, but this is the positive cycle of it, which is going to be a charging of a CDC2. Charging of a CDC2. Maybe somewhere here. It should be charging. It should be of VDC2 and VDC1. Yeah, this is a kind of a steady state operation where your load currents are this way and your filter currents are the harmonic current. You can see that the source currents are perfectly sinusoidal. Yeah, and you can see that the dynamic response of the entire the circuit. You can see that this is the PCC voltage, and you have a unbalanced nonlinear load has been connected at 0.04 seconds. You have the source currents, and the load currents are same. We didn't turn on the shunt active power filter, that is STATCOM. You can see that the source filter current is very higher over here. Here we switched on the STATCOM. Maybe it tries to take a few cycles. What is the reason for the few cycles is to measure the load average power, it takes 1 cycle of a data. Once after that, you can see that the source neutral is going to be 0. You have the source currents are perfectly sinusoidal, and the load currents are the same only. We can see that the filter currents. And when you have a non-linear loads, also this particular three-phase diode bridge load has been connected over here. We can see that uh, the source currents are perfectly sinusoidal again. See that the source filter is also there. This is a kind of a dynamic operation where we change the load and where we connected a distribution static compensator. We can use this kind of a filter, an active filter, in the microgrid, uh, uh, not wherever, if your grid, a microgrid is going to have these kind of a nature of harmonic currents as the reactive power, you can use this particular active power filter, or it is not necessary to be used this particular additional what to say, the voltage source converter. Maybe you can use where your PV integrated what to say, the voltage source converter, wherever it is there, that voltage source converter also, maybe the distributed energy resources where your PV is there, that inverter can also be used to support the real power as well as the reactive power as well as the harmonic elimination also. Okay. Yeah, these are the experimental results which shows that your source voltage and then the source current, figure 2, we can see that this is the harmonic currents and these are the filter currents. Okay. And this is a phase A, and there we have changed the dynamic variation. You can see that this particular load has been changed. You have seen that the load current of 3 over here, this particular figure. They change the load over here. You can see then still also your source current is is sinusoidal. Okay, the phase B also we change the load over this particular case 3. The pink line, you can see that the load variation is there at this point. Phase C, this one. Yeah, and you have unbalanced load currents. The source current after compensation. It was taken very long back, around 2017. Okay. We have made further modification in the setup. This is an experimental setup where we have built in our collaterals laboratory. Yeah. Regarding the experimental setup, what are the things which are required is we require to have the transducer, and for the digital signal processor, it not be digital signal processor, we can go for a FPGA or even DSpace controller, where you require to have for a DSP, it requires to have a signal conditioning circuit. If you're going for a DSpace microlab box or DSpace any kind of a device, it doesn't require your signal conditioning. Transducer circuit is enough, more than enough to have analog signal itself. And then the digital signal processor, where you used process your control algorithm, where you are going to process your signals and develop your control algorithm, and you can keep the switching pulses. The digital I go to the voltage source. Yeah, is there any questions? If you have any questions, like, you can ask now. Yeah. See, whatever I showed the results over here. Maybe it is kind of an island network. We are not connected to any grid over here, where we have taken our own voltage source and then a programmable power source, and then we can able to do it. Yeah. So far, what I have presented over here, I have presented with respect to the uh, current related power quality improvement. Okay. Now we'll try to see. Uh, Now we'll try to see the voltage quality improvement. Okay. How we are going to use the voltage dynamic voltage restorer in a micro. Okay. Yeah. These are the some of the European norms of the standards with respect to the voltage. The voltage must be 90 percentage and 110% of nominal voltage, and then voltage unbalance to be 2%, and the harmonics in the voltage is less than 8. V3 of 5%, V5 6 or V7 is 5%. Okay, and the frequency is for 50 hertz. You have a variation of plus or minus 1%. And yeah, these are the voltage distortion limits with respect to the IEEE 519 standards. Maybe these are the standards with respect to the distribution level. Maybe in the microgrid level, people have not come out with any kind of a standards, but it is very well applicable. When you take about, we are not going to have the voltages more than greater than 1 kV. We are going to have the microgrid of less than of 1 kV. Okay? So we can go for in the individual harmonic order of 5%, and total harmonic distortion is 8%. Okay. Yeah, when you are looking over the total harmonic distortion, not with respect to the current, we are looking over with respect to the voltage. Yeah. Some of the devices which can be used for the voltage quality improvement is flywheels, the supercapacitors, superconducting magnetic energy storages, and enhanced interfaces are dynamic voltage restorer, transient voltage surge suppressors, and these are the things are there. We can go for the voltage quality improvement devices. Okay. I'll try to brief about one of the voltage quality issues is the voltage sag. Okay, this particular voltage sag is a phenomena which is going to occur due to the fault in the system. Okay, yeah, you are going to have a fault in the system, maybe in the microgrid also. You are going to have a fault, a three-phase fault, a single line to ground fault, or double line fault. Okay, during that period only, we are going to have your at the point of common coupling, there is a change in the voltage. Okay, due to the source impedance and the fault impedance, you are going to have affected with respect to the voltage side. You can see further equation, equation 1. You can see that how does it is going to have the impact. As we have seen, like in the earlier beginning of the slides, where you have seen that the voltage drop because of the inductive nature, inductive current. Yeah, the same thing like which we can apply that the PCC voltage is going to change because of the fault current also. And not necessary, I mean, it is not the voltage magnitude reduction. You are going to have the phase jumps also, the phase angle shift with respect to the preset voltage. You can see this. Where is it? Yeah, we can see that this figure, you have the balanced voltage, maybe this the dotted line over here. There is a phase shift over here. Okay, because of this is a transformer connection, or because of the impedance also there is a phase shift also will be there in the B side voltage. Yeah, here is an example of the shown where you are going to have the phase shift in your the load voltage, this voltage. The fault has occurred in this particular the other side of the transformer. Yeah, in order to we'll look into the one of the example, considering that the primary side voltages is 0 at an angle of 0, and VB is 1 at an angle of minus 120, VC is 1 at an angle of 120 degrees. What we are going to see that on the load side, is it the same voltages are going to be affected, or is there something difference will be there? Okay. Looking over the type of the connection, we have a star connected transformer. So when you have the star connection, how do you study the unbalanced voltages? We try to study the unbalanced voltages by converting into the sequence components. Okay. When you do the sequence components, your the transformer of the star don't have the neutral connection over here. Okay, neutral on the either side of the transformer. So what is going to happen is the zero sequence of the voltage on the primary side is not going to transfer to the secondary side. Okay. Okay. What we are going to do was we take the primary side of the voltages, try to dissolve to the zero, positive and negative sequence. Okay. We get these voltages. Now we, as I said, like the zero sequence won't be transferred to the secondary side. So I've taken on the secondary side, the zero sequence voltage is zero. Rest of all the voltages, it is same only. The positive, the VA1 of the primary side, 2 is the secondary side of the positive sequence, VA2 is the negative side, negative sequence of the secondary side, and VA1 negative is the negative sequence to the primary side. These are the voltages. Now, when you convert these voltages to the negative sequence to the normal voltages, we see that the 0.33, 0.88 at minus 100 at 0.89, 0.88 at an angle of 100.8. See the phasor diagram of the primary side voltages and the phasor diagram of the B side and the secondary side of the voltage. You can see that the phase C having a phase shift and phase B also having the phase shift. And you have a voltage on the VA2 also. This is what it is going to happen in the when you have a transformer. You see that there is a phase shift also is there apart from your magnitude reduction in the voltage. Okay. Now what we do was there are the different types of your voltage stacks based on the type of the transformer connection. Okay. And now you can see this particular phasor, this particular system diagram. You have a single line to ground fault at 33 kV. Now at 11 kV it has become a type C fault, and at the 11 kV line, and the 11 line to 415 volts it has been categorized to it is going to be type D. See, they have just categorized the single line to ground fault as type B fault, and line to line ground fault as type C, LLG fault as type E, and symmetrical fault as type E. Okay. See, when you have a transformer like connections, fault has been occurred at the upstream voltages. When you go into the downstream, it is going to change the nature of the fault also. Not the nature of the fault, nature of the voltages, it is going to create another fault. See here, you can see that B single line to ground fault, once it transformed to the secondary side, it has become a type C, that is a LL fault. Okay. Okay. Yeah. Yeah. When these are the some of the topologies where your voltage source converter have been used to improve your voltage quality at your critical loads at a point of common coupling. Okay. We'll try to look a typical voltage source converter. How does it looks like? Yeah, this is a typical practical system of the DVR. You have a transformer where, and you have a mechanical bypass disconnections in the injection transformer. Okay. Yeah, we have a line filter over here, and then the energy storage. Okay. Yeah, I was mentioning about this particular dynamic voltage restorer can be utilized for the steady state phenomenon. Steady state in the sense, like not the steady state, a transient. Okay. Wherever, when you say a fault will be there for a very short duration of a time. Fault will be cleared within a half cycle somewhere, not half a cycle. It tries to create maybe 2 cycles, maybe few cycles also. Less than I can say that maybe around a half minute also. See, this particular energy storage, whenever there is a fault occurred on a system, complete a single line to ground, one of the phases completely outage of 0 volt. In that scenarios, uh, this energy storage used to support particular to one of the phase of the load. Okay. Suppose if it is a three phase dead fault is there, a short. I mean, if you are going to bring the voltage to be 0, then this particular energy storage will support the load also. But this, whatever the battery energy storage is there, which is connected to dynamic voltage store, it won't support for a very longer durations of a time. Like what we have in our household VPS, it has a battery. I mean, whenever there is a power outage is there, you have an energy storage which is connected to your an inverter. It supports a very few important loads, maybe the illumination load, maybe lights, maybe one of the fan. But and also your inverter which is connected, it is going to support for maybe half an hour. The normal whatever we use our UPS, it supports maybe around 10 minutes only. It can't support for the more than 10 minutes. So because of that, suppose if you are going to take a voltage quality issues, which will be going to exist for a very long duration of a time, maybe of a steady state voltage variations. In that case, this particular energy support storage cannot be supported. See, suppose when you don't have this particular energy storage, if you have any kind of a continuous power generation, okay, you have a kind of a source where it is going to be connected to a local grid, any other grid also. In that case, like it supports under voltage, over voltage, maybe what is the steady state voltage variations also it supports this. It is about a practical DVR. And why this particular thyristor bypass is required is they short during the without the sag. When there is no sag, there should not be any drop across this particular transformer. Maybe they connect to this switch also, because if you cannot have the injection transformer throughout the time, it is going to have certainly there is a drop over there. Okay. And also this particular bypass switch is there where we want to bypass completely, not to have the connection, they short it also. Okay. Either of it, either they're going to have this particular mechanical bypass disconnection, or they can go to the thyristor bypass. Okay. Design aspects I'm not going to show. I just show you, maybe the figure clarity is not much over here. You can refer this particular paper, maybe the detailed comparison of a system topology of dynamic voltage disorder, which will be used a PWM scheme. Is there a clarity with it? I think like it's fine. Yeah, here you require to have the load voltage. Maybe this particular case where you require to have the load voltage need to be measured. We can also have your what to say. You can have the reference load voltage, and you need to measure your supply voltage. And you are going to convert to the DQ transformation. You need to have the PLL. And yeah, with this, what we get was addition and subtraction over here. We get the DVR in DVR voltages. How much to be DVR voltages? Here, it is required to create a sag detection also. If it is there is no sag, then you don't require to the a load generation over here. This generation is not required. It will be a 0 only. Okay. Yeah, here what we get was we get a supply voltage and load reference. What we get was we get a UDC reference voltage. Okay, this particular U supply minus UL load, if there is a no sag, then this voltage will be 0. Okay, because your load voltage and supply voltage to be 0, so we won't get this voltage. And this operation also will won't be there. We are not going to operate your we're not going to have the switching pulses to your voltage source converter. Okay. Yeah, now what we get was we get the reference voltage UDC reference DQ over here, this particular UDC reference DQ. Yeah, when the DVR is going to operate it, we need to check is there an error between the actual reference voltage to the actual DVR voltage. If there is any error comes over here, we get over error, the feedback loop over here. This is a feedback loop. The error is going to be added to your reference DQ voltage. Okay, to your reference DQ voltage. This particular block, which is there, this is the reference voltage. And this particular block, which is there, is an error which is going to be added over here. Okay. And now we are going to convert to the ABC components and we get the DVR voltage. This DVR is going to have your reference voltage and your error also. So both the feedback and feed forward path both will be there, and you can generate your PWM string pulses. Okay. Yeah. Now you can see that we have been considered this a normal operation where there is no sag over here. Okay. Now there is a sag occurred over here. We can see that the source voltage has been, earlier it was around 3, near to the 400. Now we can see that it has been reduced further. We can see that there is a sag occurred here, 259.8. And we have created, we have used the DVR, start operating it, and we can see that the 317.8. But still we are not come out around 326. We have reached to the 370. And during the swell also, it has now the voltage has been swell. Swell in the sense like we can go for, if there is any fault, some of the faults is going to create the voltage swell. Okay. During this period, we have this voltage swell. Yeah. Now by using the DVR, we have reduced the voltage, but it is not reduced to 355, 350. The required is 326, but we are not come to that level of the voltage. Is there any questions with respect to the DVR? Do you have any questions? Do you have any questions? Yeah, we will quickly see one of another control where your unified power quality conditioner will be used for your power quality improvement or dealing the voltage and uh, current voltage and current quality improvements. Okay. Quickly see, this is a custom power devices is a DVR, the figure here, and this one we have seen so far. The DVR we have seen it just now, and we have seen like this particular figure B, which is going to eliminate your source current quality improvement, and this is the device which is used to improve the load voltage. See, in all the cases, see for this particular DVR, when you see the dynamic voltage resistor, we are not going to change the effect at the VS side. The voltage, whatever the VS is there, it is in the pure, it is in the poor condition only. If there is any voltage quality, we are just going to change the effect of the load voltage side. We are protecting your load to be. We are going to give a load a quality voltage, but we are not going to make your voltage of the source to be quality. We are going to use your the D StatCom. We are not going to alter any kind of a load current over here. The load characteristic is still the same. We are going to change the source side voltage. Okay. Yeah. Now this particular unified power quality conditioner is having the both the series and the shunt having a common DC link. And this particular DC link, it is not just the DC link. We need to support this particular DC link by using a battery connector. Why we require to have battery? Suppose when you are going for a DVR, it has to be supported with a battery. It is not, and if you look into some of the papers, they look as a capacitor, but it should be a battery only. Okay? Even when you are going for an unified power quality conditioner, instead of a capacitor, we should go for a battery only. Or the capacitor need to be charged from the external supply. Yeah, this is a typical three-phase four-wire system or a four-wire microgrid also. Yeah, I'll try to make out, take out this. maybe I will show you over here. Yeah, diagram is missing. Yeah, what this particular state feedback control is used to generate your switching pulses on. Okay? Just yeah, maybe yeah, this control you can see that there is a Z reference minus Z, which is a combination of all the state vectors. Okay, it is not about only the filter current. The state vectors, when you see that, the Z is combination of I reference and IC reference and VL reference and VCD reference and VSD reference and IL reference. These are the 6 parameters which are to be controlled by your unified power quality condition. Here, what it goes was it takes the kind of a based on the error, it goes to apply the top switch or the bottom switch of the series as well as the shunt also. Okay. Okay, U1 which is there, maybe which is U1 which is used for the series active power filter, and the U2 which is used for the shunt active power filter. Okay. It is based on the hysteresis current control loop only. Whatever we have looked into the same thing which is taken into consideration of state feedback control of UPQs. Yeah, I'll just show you the results. Okay. Here, what when I will try to show you, these are the experimental setup which has been built in during my PhD. Okay. Yeah. See, these are the results. You can see that the voltage having the sag at this point. We have created the voltage sag for a very few number of cycles. You see that this is the injected voltage at the A phase, and this injected voltage at the B phase, and injected voltage at C phase. You can see that here at the B, we can show that there is a simultaneous improvement. You can see that at this cycle, maybe there is a voltage sag at a load. I mean, you can see that this side first the figure B, we have created the voltage sag in the 1, 2, and 3, and 4, and 5 cycles. This is operation over here. The low voltage has brought to the it has brought to the required load voltage, and you can see that in all the time your source current is sinusoidal. Okay, it's also in phase with your source voltage also. Yeah, that observation can be done with respect to all the other phases, B phase and C phase. Okay. Yeah, I mean this kind of a setup which can be used in your microgrid applications also. Like this particular unified power quality conditioner, which is used to try to improve simultaneously both the voltage and the current quality also. But in general, the voltage quality, I mean, even like when you take a microgrid, we see that the voltage will be controlled. You have a voltage and frequency control all the loop. As we have seen, like the voltage and frequency control is a primary control. In your microgrid applications also, the hierarchy goes. You are going to control the voltage and frequency all the time. Okay, it tries to maintain your sinusoidal. It tries to maintain to the nominal value also. Maybe like because of the nature of your loads, you have a distortion in the voltage. But anyway, like when you're taking about a microgrid, we are going to have a more number of your passive filters which have been connected to the system. Okay, how does they design the passive filter is they looked over your microgrids and the nature of your loads which will be exist in the microgrid. Based on that, they go for the design your passive filters. Okay. Yeah, this is what we want to highlight, we want to look into that is power quality issues and analysis and its effect on microgrid. But we are not looked into the effects. Mostly, like we looked over the mitigation of the power quality issues. See, anyway, the effect is like, see, ultimately, whenever you have a current quality issues which come arises in a system, it is going to have the impact on other loads. The voltage quality, it is obviously it is going to affect your sensitive loads. Any questions? Can you show a test case with the discharge curve? See, the test case in the sense like at the when you look the discharge curve, it is not used for only the one of the harmonic. It can be used for multiple harmonic elimination also. See, suppose if you see this particular case, okay, yeah. When you see this particular case, there is no design over here. The D-start design in the sense like there is no kind of a passive filter design. Okay, it is the D-start is designed to support the maximum the reactive power which is there in your load side, in the load side. Okay, it is not designed for any kind of a particular to one of the harmonic also. See, this case, like when you look this particular currents of IF, you can see that IL current. We have a multiple number of the harmonics over here. We have not given the harmonic spectrum. Maybe if you look the harmonic spectrum, you can understand like actually, yeah, it is not there, but it have all the kind of the harmonics. See, you can see that this figure of the three, we have a multiple number of the harmonics over here. Okay, it tries to compensate your harmonics as well as the reactive current also. Maybe you can see that this figure, you can see that you have an unbalanced currents over here. Okay? It is going to compensate your source current is what to say? Source current is also becoming a balance during the unbalanced case also. This case we have considered over here only the linear load only up to here, maybe 0.12 to 0.24 operation, or maybe up to the discharge operation we considered only the balance load. Okay, this I don't know what kind of a case studies you are expecting. Okay, fine, thank you. Any other questions? Do you have any other questions? What will be the effect of EV battery in a distribution system? What will be the effect of EV battery? See, when you say about a distribution system, you are going to have an AC, and then the EV battery is effect of EV battery in a distribution system. See, whenever you have a EV battery, okay, maybe it all depends on if you are going to use having a bidirectional converter which is connected to the EV battery. Then like if you look into the distribution system, you have a filters. It is not just without having any kind of filters. They won't inject maybe what is the vehicle to grid operation. If you want to talk about the vehicle to grid operation, you have certainly a filters. It tries to filter out all the harmonics when the battery power is injected to your distribution system. Like what we have a normal UPS in your household, you are going to have what do you mean to say UPS. Definitely the UPS when you are connected a DC battery, DC energy is going to inject your grid, maybe connected to some kind of a load. Then obviously you require to have a filter. I don't think like in between the EV battery and the distribution system, you have a energy conversion, energy, when you have a power electronic converters and you have a filter also. I don't think it don't have any kind of an effect. Maybe in some cases where, especially when you're going for a battery connected of a distribution system, like there is a effect of a over voltage also. Over voltage in the sense like um, mm, if more excess power is injected to from the battery to the grid, then obviously you are going to when your load is not having a sufficient when you have an excess power, then in that case your voltage is going to be shoot. Sometimes we can use the EV battery for the peak shaving also. Okay, like uh, if your system is connected to having a very less power, and if the battery is having a very less power, in that case the distribution system is going to charge your battery. Is there any other questions? Yeah, I think like I'm going to thank you all for attending the session.